Welcome to the presentation of the paper ASIC Accelerator in 28 nanometer for the post-quantum digital signature scheme XMSS. My name is Prashant and I am presenting on behalf of our team. Quantum computers can render existing asymmetric cryptographic schemes like RSA vulnerable to quantum computing attacks. To counter this threat, NIST has already started standardizing post-quantum crypto or PQC algorithms that are resistant to quantum computing attacks. As the standardization process moves forward, the performance of PQC algorithms is becoming an increasingly important metric. Prior work on performance evaluation of PQC algorithms focus on either software or FPGA implementations. Very few works evaluate ASIC implementations. Our work focuses on ASIC performance evaluation of a post-quantum digital signature scheme called Extended Merkle Signature Scheme, or XMSS in short. We present the first 28 nanometer ASIC implementation of the XMSS scheme and compare its performance with an equivalent FPGA implementation. I will quickly introduce the XMSS algorithm before going into the implementation details. XMSS relies on hashes, in this case SHA-256, to provide security against quantum attacks. On the right, you see the XMSS computation tree. It has three main sections: Merkle tree, L tree, and the Winternitz one-time signature instances, also called Watts instances. A Watts instance, as the name signifies, can be used to sign only one message. In order to enable multiple signatures, XMSS uses a Merkle tree structure to combine multiple Watts instances. A Merkle tree of height h can support up to 2 power h signatures. Next, the Watts instance itself is made up of multiple chains of SHA-256 computations, which are depicted as boxes in the diagram. Each chain takes in a Watts secret key, highlighted in red, and applies the SHA-256 hash function iteratively. The outputs of the Watts chains are the Watts public keys, which are marked in blue. The L tree and the Merkle tree then reduce the Watts public keys into a single XMSS public key, which is the root node of the Merkle tree. This reduction is also performed using SHA-256 hash function. Going forward, we will refer to the Watts instance and the corresponding L tree as the XMSS leaf instance, as depicted by the dashed blue box. We do this as it is the most used and most compute-intensive portion of the XMSS signature scheme. The XMSS signature scheme consists of three main operations: key generation, signing, and verification. The key generation operation must generate the Watts secret keys and the XMSS public key, which is the root of the Merkle tree. Therefore, the entire tree needs to be computed for this operation. This requires 2 to the power h XMSS leaf computations. For the signing operation, the amount of computation depends on the specific Watts instance and the path to the root node. But the worst case for signing still involves 2 to the power h XMSS leaf computations. For verification operation, only one XMSS leaf computation is needed, but it is still the most compute-intensive portion of this operation. Overall, the XMSS leaf computation is the most used and the most compute-intensive step in the XMSS scheme. Therefore, the XMSS leaf computation is the perfect candidate for hardware acceleration. The figure on the right shows the high-level architecture of the XMSS leaf accelerator. The design is organized into three modules: SHA-256 XMSS, Watts, and L tree. The FSM on the left controls the I/O requests to the accelerator and sequences the Watts and L tree computation. It also controls the access to the memory module, highlighted in pink, that is used to store the intermediate results. The Watts module, highlighted in blue, has a key expansion unit. This unit generates the Watts secret keys that are inputs to the chains. The chain unit sequences the computation of the chains and produces the Watts public keys, which are stored in the memory. The L3 module reads the Watts public keys and generates a single 256-bit result, which is the output of the XMSS leaf module. The SHA-256 XMSS module computes the SHA hash function and is specifically optimized for XMSS computation. Watts and L3 modules send requests to this module when a SHA computation is needed. Moreover, SHA is the most time-consuming portion of the XMSS leaf computation. Since SHA-256 XMSS is the most time-consuming portion of the XMSS leaf accelerator, the performance of this module is critical. Therefore, we implemented a high-performance pipeline version called LeafPipe and a regular non-pipeline version called Leaf, and studied the trade-offs between the two versions. The SHA data path is in the critical path for both the FPGA and ASIC implementations. To reduce the critical path delay, we pipelined the data path into 4 stages as shown in the figure. Since the SHA computation is iterative, both versions require the same number of clock cycles, and the throughput increase in LeafPipe is due to the increased operating frequency. Now, let's look at the implementation of Leaf and LeafPipe designs. The die micrograph on the right shows the Leaf and LeafPipe accelerators implemented in an industrial 28nm 9-metal CMOS process. The accelerators occupy a total area of around 0.28 mm². The logic is synthesized using standard VTH cells, and the memory module is implemented using the foundry-provided single-port SRAM compiler. The chip has 16 IOs dedicated to the XMSS accelerators and uses two-way FIFOs to service the requests to the accelerator. Leaf and LeafPipe accelerators can operate up to 800 MHz and 1 GHz respectively. The layout capture on the right shows the placement of various modules in the Leaf accelerators. The LeafPipe accelerator is approximately 1.4 times larger than the Leaf accelerator. While the area of the SHA and L3 modules in the LeafPipe accelerator increased by 2x, the area of memory and Watts modules did not change. Now let's look at the delay and power comparison. As expected, the LeafPipe accelerator has the lowest delay and achieves the highest operating frequency of approximately 1 GHz. While pipelining decreased the SHA-256 data path delay, the frequency of the LeafPipe accelerator is limited by the slow SRAM access delay. At the highest frequency, the LeafPipe accelerator consumes around 2.3 times more power than the Leaf accelerator. LeafPipe design is most suitable for applications that need to maximize performance. But if an application is sensitive to power consumption or area, then Leaf design is a good choice. In addition to the ASIC implementation, we implemented the accelerators on the Arctic7 FPGA. On the FPGA, the LeafPipe design is approximately 1.6 times larger than the Leaf design. The LeafPipe design is also 1.7 times faster and consumes 2.4 times more power compared to the Leaf design at the highest operating frequency. Since the FPGA is implemented in the same 28nm technology node as the ASIC, we can directly compare the delay and power results. The ASIC Leaf and LeafPipe designs are 6 times and 9 times faster than the FPGA designs. They also consume an order of magnitude lower energy compared to the FPGA designs. The LeafPipe accelerator has the best energy delay and area delay metrics in the FPGA implementation, but this is not the case for the ASIC implementation. These results highlight that the architectural decisions like pipelining need to be evaluated independently for ASIC and FPGA implementations. To conclude, we presented the first 28nm ASIC implementation of the XMSS Leaf accelerator. We implemented 2 versions of the accelerator, namely Leaf and LeafPipe, and showed that the ASIC implementation is 6 to 9 times faster and consumes an order of magnitude lower energy compared to the FPGA implementation. Our results also showed that architectural decisions must be evaluated separately for the ASIC and FPGA, as there could be significant differences in the delay and energy trade-offs. Thank you, and questions.